Hello my friends, in this step-by-step YouTube video tutorial, we are going to study about basic operations that are applicable on discrete time signals. So first we'll see the theoretical aspect of operations on discrete time signal. Later on, we'll see how to simulate these things using MATLAB software. So in this video tutorial, we focus on discrete time signal addition and discrete time signal subtraction. Let's get started. After completion of this YouTube video tutorial, the learner should be able to understand what discrete time signal mean and their representation, and the learner will understand the need for signal processing, what signal processing means, and what digital signal processing mean, and their similarity as well as difference between signal processing, digital signal processing. After completing this one, the learner will understand the transformation on dependent variable and independent variable. What does dependent variable mean? What independent variable mean? And after completion of this tutorial, the learner will apply problems for transformation on dependent variables. And lastly, the student will know how to simulate discrete time signal addition as well as discrete time signal subtraction using MATLAB software. Let's get started. So the first part of our discussion is about discrete time signals. So let's define what discrete time signal mean. Discrete time signals are sequence of numbers which are defined only at integer values of n, not defined for non-integer values of n. And these discrete time signals are used to convey information. Each number, that is x of n, is called a sample. X of n may be sampled from analog signal, and it is expressed as the discrete time signal xd of n is equal to the sampled analog signal, which is equal to xa of nts, where ts is the sampling period. Signals which are discrete in time and quantized in amplitude are termed as digital signal. Example for digital signals are pulse code modulation signal, which is applicable for communication system, and digital image signals. So here in the figure, we can see that in figure 1.1, it is the representation of continuous time signal, which has continuous value on the interval a, b, whereas if you consider figure 1.2, it is a discrete time signal. Now here you can see that this value is x of 0 for n is equal to 0. For n is equal to 1, it is x of 1. For n is equal to 2, this value is x of 2. For n is equal to 3, this value is x of 3. So the same is true for n values which are located on the left hand side. That is n is equal to minus 1, minus 2, minus 3, like that. So this representation is known as discrete time signals. The notation: discrete time signals are denoted by x of n, where n is an element of z, is not defined for non-integer values, and the value of n will take from minus infinity up to infinity range. Now let's proceed to the second part, which is discrete time signal representation. Electrical signals may be represented either in time domain or in frequency domain. In time domain, voltage or current is expressed as a function of time. So the signal is represented as a function of time. Example for this one is signals measured with oscilloscope. The other way of representing signal is frequency domain representation. Signals can also be represented by magnitude and phase as a function of frequency. So the magnitude as a function of frequency, phase as a function of frequency. Such type of representation is known as frequency domain representation. Periodic signals are signals which repeat themselves after some period n. They are represented by the power spectrum. And signals that are time limited, only non-zero for finite period of time, they are represented by energy spectrum. Now let's come back to the time domain analysis of discrete time signals. Now discrete time signals are represented 4 methods. The first one is functional method. In functional representation, the signal is represented as a mathematical equation x of n, which is equal to e raised to minus n for minus 3 less than or equal to n, and n is less than or equal to 3, and it is 0 otherwise. So this type of representation is mathematical representation. The second method of representation is tabular method or tabulation method. In tabular method, 2 rows of a table are used to represent a discrete time signal. In the first row, the independent variable n is used. You can see that here. The independent variable is used in the first row. In the second row, the signal x of n for each values of n are tabulated. So this method of representation is known as tabulation method. The third method of representing discrete time sequence method. In sequence representation, the discrete time signal is represented as a one-dimensional array as shown below. Here, this arrow indicates the position of n is equal to 0. And such type of representation is known as sequence representation. The last one is graphical method, in which the signal is represented graphically. Now, x-axis represents the index or the time, and the y-axis represents the sample, that is x of n. signal processing. Signal processing refers to any kind of modification, manipulation, and analysis of signal. Signal processing has application in nearly every field of study. We can also define signal processing as it's a discipline that deals with transformation and manipulation of signal in order to extract information. These processing techniques are used to improve the efficiency of the system. So, signal processing, as we have said earlier, it is analyzing of the signal. Now, signal will be analyzed in two ways. One is time domain analysis, and the other one is frequency domain analysis. The analysis of physical signals, mathematical functions, time series of economic or environmental data with respect to time is termed as time domain analysis. Signals or function values in the case of time domain are numbers at various instant of time. Time domain graph shows how the signal varies with respect to time, and an instrument which is visualized this time domain signal is known as oscilloscope. So an oscilloscope is a tool commonly used to see real-world signals in the time domain. The next category is known as frequency domain analysis. The analysis of physical signals, mathematical functions with respect to frequency is termed as frequency domain analysis. Frequency domain analysis displays how much of the signal exists within a given range of frequencies. Frequency domain analysis includes phase shift which is necessary for recovery of the signal in time domain. Spectrum analyzer is an instrument which is used to visualize the signal in frequency domain analysis. Now let's compare signal processing with that of digital signal processing. What is the similarity and difference between signal processing and digital signal processing? So digital signal processing is a subfield of signal processing that deals with the representation and manipulation of signals in digital format. Now let's compare this signal processing and DSP. So the signal format in the case of signal processing is either it is analog or digital format, whereas in the case of DSP it is digital. The type of operation to be performed on signal, either it may be analog or digital in the case of signal processing, whereas it is in digital format in the case of DSP. In short, signal processing includes both analog signal processing and digital signal processing, whereas DSP is related to digital formats. Now let's ask one question. Why do we need to modify readily available signals? Instead of using the available signals simply, why is it necessary to modify these signals? In order to answer this question, let's see some of the topics from your chemistry course. We have element and compounds, and the property of pure element is quite different from their compounds. Now let's see some example. Consider sodium chloride, which is common salt. Sodium is group 1 metallic element and chlorine is group 7 gaseous elements. Sodium is highly toxic and chlorine is a poisonous gas. And sodium is vigorously burning metal and this chlorine is greenish yellow gas. Now what will happen if you combine sodium and chlorine? Just we will get sodium chloride at room temperature. But the property of this sodium chloride is it's non-toxic and essential nutrient for our day-to-day life. The same is true for signals. Combining two or more signals by performing any kind of operation, that means transforming or modifying, would result in a new signal. And the property of this new signal is better than that of the individual signal. Now, let's take one example. Audio signals are used very short distance communication. When you are speaking, someone across the room can hear you. On the other hand, radio frequencies are very good at propagating long distance. For instance, if 100 volts 1 megahertz sine wave is fed into an antenna, the resulting radio wave can be detected in the next room or in the next country. That means modulation is a process of merging signals to form a third signal with desirable characteristics of both. Basic operations on discrete time signals. Here we'll study only the time domain analysis parts. The basic operation to be performed in signal processing falls under two major categories. that is operation to be performed on dependent variable. So the first category includes amplitude scaling, changing the amplitude of the signal. That means increasing the amplitude of the signal or decreasing the amplitude of the signal. And the second one is discrete time signal addition, adding two or more signals to get a new signal, and discrete time signal subtraction, subtracting one signal from the other. DT signal multiplication, multiplying one signal by the other in time domain. When it comes to the dependent variable transformation, this one includes time scaling, either compression or expansion of time shifting, that means either advanced signal or delayed signal, and time reversal, that is a reflection or folding of the signal. Discrete time signal addition. Now here the operations on two or more sequences can be carried out if all the sequences have the same length and they are defined on the same range of time index n. If the discrete time signals are not defined on the same range, then we can append zero-valued samples to the sequence of the smaller lengths to make all sequences have the same range of time index. Now let's go to directly discrete time signal addition. Consider the two discrete time signals x1 of n and x2 of n. The DT signal addition operation is given by y of n, which is equal to x1 of n plus x2 of n. The DT signal y of n is obtained by adding the amplitudes of x1 of n and x2 of n at each instant of n. Now here the symbol for adder is this one, x of n and w of n. They will be added to give y of n, which is equal to the sum of x of n and w of n. Now if you have more than two input sequences, then you can have like this x1 of n, x2 of n, up to xk of nt, and the response is y of nt, which is equal to summation I start from 1 up to k of xi of nt. Now let's consider these two signals, x1 of n and x2 of n. x1 of n is equal to 1, 2, 3, 4. So at n is equal to minus 2, the value is 1. At n is equal to minus 1, the value is 2. At n is equal to 0, the value is 3. At n is equal to 1, the value is 4. And at n is equal to 2, x1 of n is considered to be 0. Now let's consider x2 of n. At n is equal to minus 2, the value is 0. At n is equal to minus 1, its value is 4. At n is equal to 0, the value is minus 3. At n is equal to 1, its value is 2. And at n is equal to 2, the value is 1. Now the sum x1 of n plus x2 of n equals 1 plus 0, which is 1, 2 plus 4, which is 6, 3 plus minus 3, which is 0, 4 plus 2, which is 6, and 0 plus 1 is 1. x1 of n plus x2 of n, which is y of n, equals 1, 6, 0, 6, 1. So using MATLAB, we can plot the input sequence x1 of n, which has a value 1, 2, 3, 4. At n is equal to minus 2, minus 1, 0, and 1. And x2 of n equals 4 minus 3, 2, 1. At n is equal to minus 1, 0, 1, and 2. Their sum becomes 1 at n is equal to minus 2, 6 at n is equal to minus 1, 0 at n is equal to 0. Application areas. A very simple application of addition operation is improving the quality of measured data corrupted by additive noise. Let DI denotes noise vector corrupting dice data. X denotes uncorrupted data vector. Then the sum of these two quantities equals Xi, which is equal to the uncorrupted data vector plus the noise vector. The average data vector, which is termed as ensemble average, it is obtained after k measurement. The average data vector, called ensemble average, obtained after k measurement, is given by ensemble average equals 1 over k summation I start from 1 up to k xi, which is equal to 1 over k summation I start from 1 up to k, the uncorrupted data vector plus the noise vector. And the average value of uncorrupted data vector equals the data vector itself plus 1 over k summation I start from 1 up to k of the noise vector. And for large values of k, the second term goes to 0, and the ensemble average equals the uncorrupted data vector. Discrete time signal subtraction. Now let's proceed to the second type of operation to be performed on the independent variable, that is amplitude. And this operation is known as discrete time signal subtraction. Consider two discrete time signals, x1 of n and x2 of n, as shown in the next slide, and the difference between the two samples. y of n is equal to x1 of n minus x2 of n is a discrete time signal subtraction operation. Now let's see this one with example. Consider x1 of n to be 1 at n is equal to minus 2, 2 at n is equal to minus 1, 3 at n is equal to 0, 4 at n is equal to 1, and 0 at n is equal to 2. And let's consider x2 of n to be 0 at n is equal to minus 2, 4 at n is equal to minus 1, minus 3 at n is equal to 0, 2 at n is equal to 1, 1 at n is equal to 2. The difference between x1 of n and x2 of n is equal to 1 minus 0, it is 1, 2 minus 4, it is equal to minus 2, 3 minus minus 3, it is equal to 6, 4 minus 2, 1, and 0 minus 1, it is equal to minus 1. Therefore, y of n is equal to 1, minus 2, 6, 2, and minus 1. So using MATLAB software, just you can simulate x1 of n, it is equal to 1 at n is equal to minus 2, 2 at n is equal to minus 1, 3 at n is equal to 0, 4 at n is equal to 1. Similarly, for x2 of n, it is equal to 4 at n is equal to minus 1, minus 3 at n is equal to 0, 2 at n is equal to 1, and 1 at n is equal to 2. So the difference between the two samples, x1 of n minus x2 of n, is equal to 1 at n is equal to minus 2, minus 1 at n is equal to minus 2, 6 at n is equal to 0, 2 at n is equal to 1, and minus 1 at n is equal to 2. Application areas. This is the general block diagram for feedback system, and particularly this one shows a negative feedback system. Now you can see that this is the feedback signal. So in control system, the process of sampling and returning the output or part of the output to the input end of the system is known as a feedback. Feedback plays a vital role in improving the efficiency of the system, and feedback is unidirectional. Now here we can see that R of S is the reference input signal and H of S is the feedback signal. The difference between the input signal and the feedback signal will be fed to the loop gain of the system. Now here, feedback in control system is unidirectional. It is always from the output of the system to the input of the system. We have two types of feedback system. One is negative feedback system or degenerate feedback system, and the other one is positive feedback system or regenerative feedback system. So in the case of negative feedback system, the reference input signal and the feedback signals are out of phase by 180 degrees, so that the error signal is equal to the reference signal minus the feedback signal. An example for this one is amplifier circuit. So the second type of feedback system is a positive feedback system, in which the reference input signal and the feedback signals are in phase. So the input signal for the open loop gain of the system is equal to the reference signal plus feedback signal. So here we can see that the two signals will be added. An example. Now let's proceed to the MATLAB. The MATLAB has two parts. One is function definition and the other one is function calling. And the file name for function definition is sigadd.m, and the aim of this program is to compute discrete time signal addition, that is x1 of n plus x2 of n. Let x1 represent the discrete time signal x1 of n and its index is n1. Let x2 represent dt signal x2 of n and its index is n2. Let y represent the discrete time signal y of n and y of n is equal to x1 of n plus x2 of n. Let n represents the duration of dt signal y of n. So function y in square bracket y comma n is equal to sig add x1 comma n1 x2 comma n2. The output arguments are y and n. The input arguments or the input parameters are x1, n1, x2, and n2. Now the output argument n is defined as we have minimum value for n1 as well as minimum value for n2, and the minimum value for n is the minimum of the minimum value of n1 and minimum value of n2. So out of the two minimum values, the minimum is taken as a minimum, and the maximum value is maximum value of n1, maximum value of n2. N is defined as, so the range for n is starting from minimum value up to a maximum value. Let y1 will be a row vector with all its elements are zeros, and the length of y1 is equal to length of n. And on the next line, copy the content of y1 into y2. Copy the content of x1 for those value of n which is greater than or equal to the minimum value of n1, and n which is less than or equal to the maximum value of n1. Or copy the content of x1 for n values which satisfy the following condition: n should be greater than or equal to minimum of n1, and n should be less than or equal to maximum of n1. Copy the content of x2 into y2 for those values of n which satisfy the following condition: n should be greater or equal to minimum of n2, and n should be less than or equal to the maximum of n2. Now this one will help us to append zeros for those values of some x of n in which it has lower in size the value of n. Now we have copied the content of x1 into y1. We have copied content of x2 into y2. The length of y1 and y2 is n, and we can add the corresponding values or the corresponding amplitudes. Y is equal to y1 and y2, which is another output argument. And this one will end the definition of the function. Now save this one with the file name sigadd. Now let's proceed to the next part. The next part is function calling. Clear all, close all, and CLC. On step 2, accept the input dt sequence x1 of n and x2 of n. That is, accept the input argument x1 of n and its index n1, x2 of n and its index n2. Step 3, function calling y of n, which is equal to x1 of n plus x2 of n. Just we call the function sigadd with input arguments x1, n1, x2, n2, and we'll display the results. The next part is plotting the input sequence x1 of n. The input signal x1 of n and x2 of n is taken from the slide. Now let's plot the second signal, that is the input signal x2 of n.